Hi, B-Scout. These are your day 93 notes. Today we are talking about more integrals with trig powers, but we're going to move on and talk about what happens when there is an even power up there. You already know the rules for sine squared and cosine squared. We're going to use some double angle identities and do some replacements. So these are the two important replacements that we'll need for some of our work today when we're talking about even powers. So make sure you're confident and comfortable with where those come from. But then from there, it says, can you repeat these from yesterday? I'll leave it up to you. If you think you want a little bit more practice with some odd powers, here's cos cubed and cos to the fifth. I'll kind of show you the logic and the procedure for these next time we're in class. So if you need a little bit of assistance, let me know. But otherwise, if you want some extra practice, there's cos cubed and cos to the fifth again. So let's kind of jump right into the new stuff then. If we look at, for example, sine squared. What we just saw for sine squared is using a double angle substitution. We know that this is the same thing as 1 minus cos 2x over 2. So then from there, we could break it up to 1/2 minus cos 2x over 2. And if we integrate both pieces, you'll get 1/2 x minus the integral of cos 2x is sine 2x. But we're going to have to divide by 2 there, so it's going to be sine 2x. Now all over 4 with the 2 already down here, and then plus c. So this is an integral that we've done in the past. If we look back a couple packets ago, we would have seen the integral for sine squared. Well, let's move on to a larger even power. What about something like cosine to the fourth? Well, the way we're going to approach this is we're going to replace cos to the fourth with, we know the integral for cos squared, so why don't we start there? Let's make it cos squared squared. And then cos squared, we're going to replace that with, from the double angle identity, 1 plus cos 2x over 2 squared dx. All right. So building from here, we now want to square this, and squaring the denominator is going to make that a 1/4. So I'm going to pull the 1/4 to the front. And now I need to square the numerator, which would be 1 plus, we're going to get 2 cos 2x's in the middle, plus then a cosine squared of 2x. Okay. So when we look at the expanded form of 1 plus cos 2x squared, we know how to find the integral of 1 dx. We know the integral of 2 cos 2x dx. And then the only thing we have to then think about, oh wait, cos squared, we also know how to find the integral here, right? So we have to use another double angle substitution. So it's going to be 1 plus 2 cosine of 2x. So the double angle substitution here is that it's going to be 1 plus cosine of double this angle, right? So since the angle is already 2x, it's going to be cosine of 4x over 2. So when I do that double angle substitution for cos squared of 2x, just make sure it's 1 plus cosine of double the angle on the inside here, 4x, and then over 2. All right, now we've set the stage that we can actually go ahead and find the antiderivative of each of these pieces. So we get 1/4. The antiderivative of 1 is x, plus the antiderivative of cosine 2x is going to be sine 2x, but then divided by 2. Well, with that 2 out front, we're just going to get a plus sine 2x. Separate this into two pieces, right? That would be 1/2 when I separate, so that's going to be a 1/2 x, which of course we can combine some like terms there. And then for the last piece, the integral of cos 4x is sine 4x, but you're going to have to divide by 4 out front. So that's going to be a plus sine 4x now over 8. Okay, so just make sure that last piece, it's probably easy to lose a quick constant there, but integral of cos 4x is sine 4x over 4 with the 2 down there, that makes it an 8 total. So combining the like terms with those x's and then multiplying through by a 4th, you wind up getting 3/8 x plus sine 2x over 4. And then at the end, plus sine of 4x all over 32, and then plus c. So even powers, not necessarily too challenging for us as long as we're confident with our double angle substitution that we've used for cos squared. You're going to do a very similar process if it was a sine to the fourth. Okay, so odd powers do tend to probably be a little bit more straightforward, but as long as we're good with making, like I said, some of those substitutions along the way, eventually breaking it down to an integral that we can evaluate hopefully pretty easily. All right, so that would be the final result for something like cosine to the fourth. Which brings us to sine to the 6th. Okay, get ready for this one. Now, as I go through this, if you need to pause along the way, because I'm just going to actually reveal one step at a time what the process and kind of talk you through it here. Okay, but if I'm going too fast, you guys know what to do at this stage in the game. All right, here's what we're going to change it into. How about sine squared cubed? That's an easy first step. So then we're going to use the double angle identity substitution for sine squared that we saw earlier. 1 minus cos 2x over 2 cubed is what we now have on the inside. Well, the tricky part here, of course, being that when I cube this, it's not as easy as just squaring it like I did for cosine to the 4th a minute ago. 2 cubed on the bottom is going to get pulled out as a 1/8. That's fine. But 1 minus cosine 2x cubed is then what we're left with on the inside. And you can see the path that I'm going to head down. I'm doing binomial expansion. Binomial expansion is a topic you learned about in pre-calc honors, maybe not for too many days in a row. So if you remember the process for binomial expansion using Pascal's triangle, these are the coefficients of something to the 3rd power. I'll show you how those coefficients play a role into what the expansion looks like. But otherwise, you got to multiply this by itself 3 times to get what that inside piece looks like. Are you ready for the expansion? Here's what it looks like. Okay. So you can see those coefficients from Pascal's. We got the 1, the 3, the 3. I didn't write down the 1 over here. But what happens with binomial expansion is the first term of the binomial gets raised to the 3rd, the 2nd, the 1st, and eventually to the 0 power. The second term in the expansion, which I'm considering to be negative cosine of 2x, starts by being raised to the 0, the 1st, the 2nd, and eventually the 3rd, the last term. So now what I'm going to do is I'm going to simplify each of those terms individually to get this is the results. Okay. So this whole thing is just 1. Then we get negative 3 cosine 2x for the next term. When I square that negative, a plus 3 cos squared, and then minus cos cubed at the end. All right. So if we treat each of these as one individual piece of the integral, some of them are easy to integrate, some of them not so easy. Here are my suggestions for each of those 4 pieces. Integrating 1 dx. Yay, that's easy. Well, the next part, minus 3 cos 2x, also pretty easy. All right, for 3 cos squared of 2x, if it's a cos squared, we know we can use a double angle substitution. Remember, we're doubling the angle 2x, so it's going to be a 4x when I make that substitution in a second. And then at the very end, we have an odd power in the mix. So how are we going to integrate an odd power? Separate one cosine from that group, and then use some u substitution with the Pythagorean identity here. Whoa, holy cow. You're ready for what the next step looks like? All right. So here's what we've got. Oh boy. All right, so I left that as a 1. Left the easy part, negative 3 cos 2x. This, I just made the double angle substitution. It would be 1 plus cosine of 4x over 2. So that's why I have a 3/2 out front. But when I double this angle and I use that identity, it's going to be a 1 plus cos 4x on the inside. That's all fine and good. Okay. The end here, though, when you do cos cubed, this is what you maybe filled in at the start of today's notes. Okay, the integral of cos cubed, make it cos squared times cos. Change cos squared to 1 minus sine squared. Do a u substitution, where u is sine of 2x. And then eventually you can integrate this much easier than what we're currently looking at right here. Okay. Now I'm not going through the whole process here of showing you what this end integral would turn out to be with our u sub, but I'm going to write down in the next step the integral of each of these pieces. Okay. Integral of 1, x. Integral of cosine 2x is sine 2x, but we got to divide by 2. This is going to be a 3/2 x. Integral of cosine of 4x is sine of 4x, but oops, divided by 4. Now it's a 3/8. All right, and then from the u substitution that we're going to do with cos cubed at the end, these are the remaining terms that you would get after integrating 1 minus u squared, subbing back in. There's a lot going on here, isn't there? Okay. Again, I kind of shortchanged you on a little bit of the work here, but it is work that you're familiar with of how to integrate cosine cubed. All right, so with all these remaining terms, there are some like terms to combine. There's these like terms. There's actually these like terms with sine 2x if you want to combine those. And then you got to distribute the 1/8 through. So when we kind of clean things up a bit and then distribute the 1/8, this is the final antiderivative for sine to the 6th. Holy cow. And again, I understand that there's a lot going on there, okay? If there's a part of this process that went too fast for you, hopefully you hit pause. If there's a part of the process that you still don't really get, then check in with me next time we're in class. But that is the antiderivative. Should we check by finding the derivative? Well, I'm going to hold off on that. The derivative is actually quite tough to find. It doesn't seem so bad, but with all the chain rule steps that we're going to have to find, it's going to be a lot of work to eventually get back to sine to the 6th. So trust me that this is the antiderivative for now. For ones that are easy enough, of course, you can check with that derivative step. Okay, so that's the most intense one for today, I promise. Sine to the 6th, a little intimidating. But let's move on to the next application question. So the next one says, find the area between the curve y equals sine to the 4th x cos to the 5th x. And we're going to find that area bound by the x-axis from 0 to pi over 2. Okay. So if we're integrating from 0 to pi over 2 along the x-axis, I'm just going to set up the integral here from 0 to pi over 2 of sine to the 4th times cos to the 5th dx. All right. So with sine and cosine both as being a part of the product on the inside here, where we have that cosine to the 5th with that odd power here, we know that this one's pretty easy to integrate. Remember, you can't separate a product into two different integrals, okay? Unless you're trying to use integration by parts, okay? But that's not really a good option given these are the two functions that we're multiplying. So watch what happens though if I try and do some separation here where I separate one cos from the group of cos to the 5th x. So it's going to be 0 to pi over 2 of sine to the 4th times, let's make it cos to the 4th times cos. Okay. And then following the process for just cosine to the 5th, I would then replace cosine here with 1 minus sine, or I guess this is cosine squared, right? Because before we get to that Pythagorean substitution, maybe it's nice to write that as cosine squared. And again, cos to the 5th is something that maybe you've already tried on the front of today's notes. Well, what's cosine squared? Cosine squared, now I can at this point replace that with 1 minus sine squared. Okay. So with some substitutions along the way and some creative splitting up of terms here, we now, I think, are well within our rights to, let's go ahead and do a u sub with sine x. And the nice thing about doing a u sub with sine x is that we already have sine out front, so we can replace that in terms of u. But when we choose u to equal sine x, we know that du very quickly becomes cos x dx. So we have our du at the end. We can replace both of these sine terms with u, and then be able to integrate from there. Okay, so let's just change the bounds real quick with respect to u, because sine of 0 is 0, sine of pi over 2 is 1. That would just make life a little bit easier now that we're going to write u to the 4th times 1 minus u squared, and then we know we have our du at the end. Okay, we've now simplified the algebra to be something where we square this. We'll distribute the u to the 4th in, see what we get there. So it's u to the 4th times 1 minus 2u squared plus u to the 4th when you expand that binomial. All right, and before you do anything else, definitely distribute that u to the 4th in, so we get 0 to 1. This is going to be u to the 4th minus 2u to the 6th plus u to the 8th du. And now we're at the stage where we can nicely take the antiderivative with some anti-power rule. So we get u to the 5th over 5 minus, this is going to be up it by 1, so 2/7 u to the 7th plus u to the 9th over 9. And we've got our really nice bounds from 0 to 1. Plugging in zeros for all the u's is going to be subtracting out 0. So we just got to plug in the 1. So it's 1/5 minus 2/7 plus a 9th, which simplifies to, with a common denominator, 8 over 315. So approximately a really tiny area here. Approximately 0.025 square units of area. All right, so it looked pretty intimidating to start, I think, with the sine to the 4th and cos to the 5th. But following that process for odd powers with cos eventually leads you to a nice u sub for sine. And if the other part of the integral has sine in it, well, then we can use that same sort of u substitution there and follow the process down. Okay. We're going to do one more application in today's notes, and that will be it for today. The last one we're going to take a look at is finding the area under the curve y equals tan to the 4th x. And we'll do this from 0 to pi over 4. So we can start off just really quickly, same way, definite integral from 0 to pi over 4 of tan to the 4th dx. Okay. Separation here is going to be a little bit different. So the patterns that we see for sine and cosine with odd and even powers, we know that those don't necessarily hold true as nicely always for tan. So what we got to think about tan is making some substitutions that are Pythagorean related. And we know that tan squared is the same thing as secant squared minus 1. Okay. So you have a few options as to how you can go about this. I'm going to creatively here write this at first as tan squared times tan squared. That's, of course, tan to the 4th. And I realize that that's the same thing as tan squared squared. But what I'm going to do is I'm just going to replace one of these tan squareds with sec squared minus 1. So the second one here, I'm going to rewrite that as secant squared minus 1. And you'll see the advantage to doing that in just a moment here. So I'm going to write from 0 to pi over 4. One more step of distributing that tan squared across to get tan squared secant squared minus tan squared dx. Okay. The advantage to having it in this form is that I'm going to now separate this into two different integrals. One of tan squared secant squared, and the other with just minus the integral of tan squared. Now, the integral of tan squared we've actually done a few times. So if you remember the trick for that one, that won't be so bad. And then over here, we actually have a nice, oops, I need a dx there. We actually have a nice u sub, because if you're recognizing, okay, the derivative of tan is secant squared, why don't we let just then u equal tan x, so that my du winds up being secant squared dx. So nice u sub over here if we let u equal just tan of x. Now, if I'm going to use that u substitution, let's change the bounds real quick. Tan of 0 is 0, tan of pi over 4 is 1. So here's your du right here. If u is tan x, it's u squared du. Okay, so that's the first piece. Now, the trick over here is that if you change tan to, again, sec squared minus 1, this is much easier for us to integrate. So it's going to be minus, well, the integral of secant squared is tan x minus the integral of 1, which is just x, and we can leave the bounds of 0 and pi over 4 there. We didn't have to use a u sub over there. Okay, integral over here is u cubed over 3 from 0 to 1. Okay, and then minus from that, if I plug in pi over 4, tan of pi over 4 is 1. And then I'm going to subtract pi over 4 from that, so it's 1 minus pi over 4. Minus, when I plug in 0 for the lower bound there, tan of 0 is 0, and then I'm going to plug in a 0 there. So that kind of zeroes out. Okay, one step away. Now just do the u sub. Plug in over here. It's going to be 1/3 minus 0. So it's 1/3 minus the quantity, 1 minus pi over 4. And if I distribute that negative in there, you're going to get a positive pi over 4. 1/3 minus 1 is now a total of negative 2/3. And this would be square units if we're talking about area. Okay. I don't want you to look at this and say, oh, how, that this is an easy example per se, but with more practice, you'll start learning the best ways to separate trig functions, whether they're to odd powers, even powers. Again, sine and cos have different patterns than sometimes what I would approach with tangent to a large exponent. But start looking for some of these patterns to pop up in other examples. And hopefully you'll be able to use some of these questions in the notes as models if you get stuck. Okay. The last page, by the way, of day 93, we're going to save that for class, so we'll do a little bit together next time I see you. If you have any questions, I know there was a lot thrown your way today, please let me know next time I see you. Otherwise, have a great rest of your day.